Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos, and we're going to be doing a GCSE combined science and physics topic whilst we have a look at waves. Specifically, we're going to be doing what I consider the introductory lesson to the topic of waves, that being the properties of waves. So our learning objective for today, our main outcome, is to be able to draw, label, and describe the features of a waveform. So we're going to learn what a waveform is, learn about the various properties of waves, and then put the two together to create a labeled diagram with the descriptions. So that's sort of our aim for today. Now, of course, there is a lot more to waves than just this. For example, there's a lot of calculus that comes a bit later, and I am more than open to exploring those in future lessons if you would like. Let me know via the comment section down below. If there are solutions to any exercises that we do throughout the lesson, then they will be linked at the top of the description. I will indicate when to click on those if you are following along. Make sure you have a pen and paper or a suitable writing or notes-taking piece of equipment. And if you are particularly doing it on pen and paper, I suggest you also have a pencil and a ruler so that you can do any drawings. If you're doing this on a computer, you may want to do screen grabs at certain times to make sure you get all the relevant diagrams. But that should be all set up. Make sure that you're ready, comfortable, maybe you got a cup of tea, don't know. But with that all said, class is in session. Let's begin. So to get us started off today, since I'm treating this lesson as sort of a topic starter, I'm not going to be doing any recaps on any prior learning in particular. Instead, I'm going to give you now a few very important bits of terminology that we're going to come across throughout the lesson. And what I'd like you to do, maybe just take a minute before we move on to have a think about what you think those words mean, and also in terms of waves, what they might mean. So the words I'd like you to think about are frequency, amplitude, wavelength, and pitch. So some of those words you may know from previous lessons in your schools. Some of them you may never have seen before, or some of them you may never have seen in the context of waves. So have a think about what those words might mean to you just for a minute, and then we'll get into sort of defining the properties of a wave. So now that we've had a little bit of thinking time just to get our brains ticking over before the start of the lesson, let's get into the meat of things and have a look at waves and waveforms. So there are many types of waves in this world. Sound waves, water waves, electromagnetic waves, many types of waves, and no, Mexican waves is not one of them, though it kind of also is. And we typically represent a wave by drawing a waveform. So we represent waves by drawing waveforms. And what these waveforms allow us to do is interpret and work out different properties of the wave. This allows us to work out or read off, and I'll put that in sort of quotes, properties of the wave. So what I'm going to do now is I'm going to draw a sort of sample waveform. And this is going to be for what we call a transverse wave. Now, there are different types, as I said before, and we're not going to address them really today. But you should be aware that there are other types of waves that exist. Anyway, so a typical waveform will look something like this. You may or may not have a line here, and you will probably have a line here. Now these may just be lines, but particularly if you get up to A level with waves, and certainly up at higher physics, then you will be labeling these as well. So this could be in some ways an axis, a set of axes if you like. So I'm going to call this the displacement, which I'll explain in a moment. And this axis can have one of two names. So either it can be the position, or it could be the time. Because waves move. Waves propagate through things to get to where they're going. So sound waves travel through the air to reach our ears, and that takes time. And it also means that the wave is in different positions at different times, and that allows us to get different information. You may or may not have these axes labeled, but if you were to label them, that's what they mean. And your waveform, for a transverse wave at least, will look something roughly, it'll be sort of translated a bit sometimes, something like this. Wow, I've actually done that. To be fair, you should really do this a little bit neater than that, but I've done that just blind and got away with it. Try and do it as neatly as you can, and that's a sort of sample wave form. So let's put some labels on this, and then we'll get into actually defining our wave properties after that. So this axis right here, we call this the rest position. So what that means, that's this line, that is where the material or space or particles would be sitting if there were no waves. The easiest way to represent this is with sound waves and air particles, because sound waves is kind of like a slinky. You push the waves along and it causes the air particles to sort of move along through vibrations, if you like, and that displaces the particles. If you think about light waves, electromagnetic waves, then they cause the material they're traveling through, which may be nothing at all, to oscillate sideways, up and down like this. And actually, you'd have two sets of waves, which you don't do until degree, so don't worry about it. That's why light can travel through vacuums and sound can't. And that means that if there were no waves, then your medium, if you like, would just be sat on this line. If you imagine space as one-dimensional for a second, all of space would be sat on this one line. And then a wave comes along and forces that space or that medium to be displaced and moved either this way, or that way, sort of, depending on the exact orientation of the wave. But we're just going to say it displaces it up and down for the moment. And that is labeled, and I'm going to be very careful with my arrow drawing here, as the displacement. So how much the space is moved is called the displacement, and that is represented by this line. So the displacement from the rest position is shown by the waveform. So the displacement at this position or this time is here, the displacement at this position is here, and so on and so forth. But there is a special name if you are at maximum displacement. So I'm going to be very careful again with where I draw my arrow. So at maximum displacement, we call that the amplitude, which is one of the words that we met earlier. And you may also see that referred to, in particularly the case of sound, as the volume, because it is linked to volume in terms of not like three-dimensional volume, like sound volume, like crank up the volume. If you have a higher amplitude on your wave, then the sound being produced by that, if it's a sound wave, is louder. So amplitude and volume are sometimes connected together, but typically the highest displacement is called the amplitude. The last one that I can label very easily is these. So these are your troughs, because they are the bottom of the waveform, and these points here are called peaks. Now you may also see them referred to as crests in certain specifications or in certain parts of the world. You may see them called crests, but at least on the specification I use, we call them peaks. So the tops are called peaks, the bottoms are called troughs, And that is everything that you can say about the waveform by looking at it. But there is one more property that we can actually intuit, and I'm going to just rub off this, and then we'll have a labeling exercise later, don't worry, so you'll get to get this in your notes. And that's this distance right here. So this distance here is the distance from one trough to another. And I will make some notes after this that I'll let you take down. So don't worry if you're sort of scribbling along with me. So as you can see, the wave repeats itself. The waveform repeats itself. So if I cover this up, that is what we would call a cycle of the wave. It starts sort of here, moving upwards. It goes up, down to the bottom, and then back up again. And then, if you look at this one, it's the same again. It repeats itself. Doing flipping miming strats there. So you've got these little cycles, and each of those cycles repeats infinitely and gives you information about two things. You can learn from it either the wavelength, or, which is why I've written them in red and green, what we call the period. And it depends on what's on this axis if you've got axes. So if you've got position on that axis, on this horizontal, then that is the distance between one trough and another, or equally one peak and another, aka the length of one cycle of the wave, aka the length of one wave. So this distance here, see, it's that length. I'll try and keep my thumbs in the same place. If I translate that, that is the length of one of those wave cycles. So it is the length of one wave. So it is the wave length, if you like. And again, I'll give you an exercise to properly match this up in a moment. However, if you have this axis being time, say seconds, then this is the time it takes for one cycle of the wave to happen. So in this time, one wave has happened or has passed a point, if you like. So you'd say you're at a point in space, and over this much time, that much wave comes past it. So that is the time period of the wave. And from that time period, you can work out the frequency, which in turn affects the pitch. I realize I've said quite a lot there. So what I'd like you to take down before we move on is this segment. If you want to do a sketch of this, you are welcome to, but we're going to do a proper exercise to label up a waveform later in the video, so you don't have to right now. I suggest, though, that you refer back to this segment when it comes to that labeling exercise if you are struggling. Right, I'm going to give you some actual clear, concise notes to take down, and then I'll let you have a go at matching up some terms to their definitions. So, just to take everything I've been saying for the past few minutes and sort of condense it into some baseline notes that I'd like you to take down. So, there are two main bullet points to consider when it comes to waveforms and waves in general. So the first is that the medium that the wave is moving through is displaced from its rest position by the wave. So when I say medium, that could be air, could be water, could be space even. Some waves don't even need a medium. For example, light can travel through things without a medium, but we're not getting into types of waves today. But there are many different media that a wave can travel through. And when the wave moves through it, that medium is displaced. So it is moved by the wave. So if you had some air particles just here in like a box of sorts, and a sound wave came through it, the air particles would move as a result of that sound wave. You might have heard about the idea of the air vibrating to carry the wave to your ear. And it starts in that rest position, and then the wave comes along and moves it or displaces it, and the maximum displacement is called the amplitude. We'll do a little thing on defining terms in a moment. And the second point is that the wave repeats in a cycle. So a wave is not just, if you like, one solid line moving along. The wave repeats itself over and over. So in the case of a sound wave, you get sort of movement like that as the air particles go back and forth. With the wave we drew earlier, we had this sort of shape, this sort of what we call a sine wave shape, and that repeats over and over and over and over. It repeats infinitely in that cycle. The length of that cycle in terms of a distance is the wavelength, so sort of the distance traveled in one cycle, and that takes a time known as the time period to go through one cycle. So as a wave is moving along, then after one cycle has happened, it has taken a period's length of time and traveled a wavelength's worth of distance. I'm going to give you one little extra definition here, and then I'm going to let you loose to have a go at doing some matchup on your own. So frequency is a word that we have seen earlier, and that is defined as the number of waves per second in shorthand. So if you think about the idea that a wave takes one time period to go through a cycle, if you were to stand somewhere and watch a wave go past you, the frequency is how many waves go past you, or you could say the number of cycles that go past you in a second, or how many vibrations all the way up and down and back to the middle again you get in a second. And that is the frequency. It's a very important term, and you often use the frequency in calculations more than you do the time period. They are linked together, and I'll mention it later how they're linked together. But for now, I'd like to give you a bit of time, because I've been talking, I realise, for the past sort of nearly 15 minutes about stuff, and I'd like to let you loose and have a go at something. So coming up on screen in a moment is a series of key terms related to waves that we have met so far. And on the other side of the screen will be a series of definitions. What I'd like you to do, if you're writing on paper, is draw that table out and match them up. Or you can draw lines to match them up, or you can rearrange them into the right order and write them correctly in rows. If you are on a computer, then I suggest you screen cap it and draw lines between them, and then check the solutions video in the description in both cases to make sure you have the correct definitions into your final notes before you go forward. So, exercise coming up on screen, link to the solutions in the description, and when you've done that, we'll have a look at transforming a waveform. So now that we've got those wave property definitions done, reminder, check the link in the description so that you've got that all happy in your head before we move on. Let's have a look at what happens when we start twiddling with wave properties. Now, in an ideal world, I would do this with an oscilloscope, which is a device that you can use to display a waveform, and then you can mess with it with a signal generator. Sadly, that's a bit of an expensive piece of kit to have lying around, so I don't have one. But if you look up videos on the internet with oscilloscopes and how they display waveforms, you could probably get a rough idea of what I'm about to talk about. So, when it comes to transforming a waveform, there are two main things that we can change. Well, in many ways, there's three, but they boil down to two different things. So the first thing we can change is the height of the wave. And the second thing we can change is the length of a cycle, and therefore the number of waves, say, on screen. So you might imagine for a moment, say, that this is like my oscilloscope, that's a hard word to say quickly, that this is my oscilloscope screen. So I could change how big the waves appear on the screen and how many of them I can fit on the screen, how closely packed together they are, by twiddling with a couple of different wave properties. So, the first of them is the amplitude. So the amplitude affects one aspect of the wave, the watt. Give yourself 30 seconds, have a think about it, and think about what changing the amplitude will do to the wave. Pause the video. So hopefully you've had a bit of a think about that. And now what the amplitude affects, you remember that by definition, this is the amplitude, which I'm going to label with a capital A. So the amplitude is the maximum displacement of the wave. Remember that definition that we've talked about a couple of times. So what that affects is the height of the wave, or you should say really the height of the peak. So if you change the amplitude of the wave, you end up getting a different height on your peak. However, where the wave is will not change. So if I was to say increase the amplitude, then my wave would now look something like this. And notice where it is. So you'll notice that so this is with A2 greater than A1. Let's label this green arrow as A1. So if I have a greater amplitude on the wave, then the height of the peak increases. However, you'll notice that the length of the cycle of this dotted wave is the same as for the solid black line, because the amplitude does not affect that. So on this, you'd see as an axis would either be time or position. And to affect that, we affect it in two different ways. Normally, by changing the frequency. So remember that frequency is the number of waves per second. I'm going to use the slash to say per because it's faster. So if I was to change the frequency of the wave, I would affect how much space a wave takes up. It's like changing the wavelength, but normally it's a bit easier to change the frequency than it is to change a wavelength. So I'm going to give a little bit of maths. The frequency is 1 over the time period. Therefore, frequency up is equivalent to saying the time period goes down. So if I was to increase the frequency, I would change the time period of the wave. So I take this one over here. That has a time period I'm going to call T1. That is the time period of that cycle, because it's the time it takes for one full cycle to happen, remember? Now, if I was to mess with it and say I increase the frequency, watch what happens. Sorry, I'm going to be very quiet while I get this right. So you can see there with my new red line, I now have a new time period, which is from there to there, and I'm going to call that T2. So T2 is less than T1, which means that because frequency is 1 over time, if you increase one of them, you decrease the other. So in this case, T has gone down, so F has gone up. So the second frequency is greater than the first frequency. And I'm using a lowercase f. If you do this at a higher level, you may see a different symbol, but I'm going to use lowercase f. I hate the fact that I can mark my own pen work. So if you increase the frequency, then the amount of waves you can fit in the same space goes up, because the time period of the wave of one cycle has gone down. This would also be the case with the wavelength. If you reduced the wavelength, so if you had this middle wave, that's got a wavelength. If I was to make that wavelength shorter, then suddenly a wave fits in this much space or this much space, or this much space, you might say, rather than that much, which means that the wavelength has changed and the appearance of the wave has changed. But notice, I've maybe not got it absolutely perfect, the amplitude of the wave has not changed. So if I was to just draw a quick little line across here, you would see they have the same amplitude, because the only thing I've changed is the frequency or the time period, or theoretically the wavelength, but that doesn't affect the amplitude of the wave. What it does affect, however, is the pitch. So a pitch of a sound, this particularly applies to sound waves, is actually affected by the frequency of the wave. If the wave is of a higher frequency, then the pitch of that sound goes up. So if you hear a high-pitched sound or a high-pitched instrument, that sound wave has got a higher frequency than the lower pitch sound, which has a lower frequency. And you would be able to hear this if you hooked up your oscilloscope and signal generator to a loudspeaker. You'd be able to twiddle with the frequency and hear the effect of the pitch. But unfortunately, I haven't got the kit to do that. There may be a simulation you can look at online. If I can find one, I'll see if I can stick it in the description. So those are the main things about transforming a waveform. I'll just put the wavelength thing in the middle so that you can see what I mean. So the wavelength symbol is a weird one. It's not a W. It's actually a Greek letter, which we call lambda. Don't know why, it just is. But if you change the wavelength of the wave, then watch what happens. I'm going to make this one a shorter wavelength as well. So you would get, again, you get the same amplitude as before, but your wavelength, lambda 2, has changed and is now shorter than lambda 1. So the wavelength does not affect the amplitude. The frequency does not affect the amplitude, but the amplitude does also not affect the frequency. These two are more tied together, period and wavelength, and you do that in a separate lesson, which I'm tempted to do about wave speed and things like that. So if you want to copy any of that down, good chance for you to do so. I realize I've been talking for another 10 minutes. So coming up on screen, once you've taken these notes, is an exercise where I'd like you to label a waveform with its various properties. You might not be able to use all the ones we know, but label up the waveform diagram. You may need to draw it or screen cap it, whichever. And there'll be some questions underneath that waveform to follow about transformations. Again, the solutions to that will be found in the description, where you can have a look on that and make sure you've got the right things into your notes before we wrap up for the day. So, to wrap up today's lesson then, I want to return to the very beginning and those words I gave you just to think about in terms of waves right at the start of the lesson. They were amplitude, wavelength, frequency, and pitch. And from what we've done today, you should have a better understanding of several of these terms, if not all of them. So, we're just going to spend a little time now just adding some extra notes to them, making sure you've got the definitions in your notes, and maybe adding some extra details if you think I say something that would be a benefit for that. So, starting off, we have the amplitude. Let's go first by its definition, which is, of course, the maximum displacement of the wave or the particles from their rest position. So you remember our waveform had its rest position, which I'm going to draw with a dotted line here. And if your waveform looked something like that, for example, a classic sine wave, then your amplitude would be the maximum displacement. It can be in the positive or the negative direction. It doesn't really matter. It is the maximum displacement of the particles from the rest position. So this, if I just draw this with a green arrow, this would be a displacement, but only the maximum displacement, would be the amplitude. So if you see this with smaller arrows, that's called the displacement, remember, and only at the peaks and the troughs do you find the amplitude. Speaking of peaks, let's talk about the wavelength. So the definition that we often give for wavelength, if this pen wants to behave, is the peak to peak distance. So if you have a waveform that looks something like 1, 2, 1, 2, that is a terrible waveform. You will draw a better one than I've just done. Let's just curl that off a little better. So the wavelength would be the distance between two peaks. I'm going to call it lambda because that's its typical symbol for particularly mathematical calculation, which we could do another time. You could also measure it between the two troughs and it would be exactly the same. In fact, as long as you measure it between two identical positions on the wave, technically it's the same, but we always measure it peak to peak because that is the easiest one to measure. And if you think about it this way, that is the distance of the length of one full cycle of the wave. So so this sort of wave here is one cycle because the sort of shape of the waveform is back to where it started. It started moving up, down, and then back up to the rest position. And if it carried on, it would go up again like it did here. So that is one full cycle, and that is the distance of the wavelength. In fact, to make that even more clear, I can pop it here and say that that is also the wavelength because it's gone through one full cycle and it's going to do the same thing again. Same thing here. It's down to the top, to the bottom, to the top, to the bottom, to the top, and that's one wavelength. Now, the frequency is very much tied up with the time period. And in terms of its definition, it is the number of waves per second passing a point. So if your wave is traveling along through space or a vacuum or the air, and you were able to sort of hold a point and count the waves as they went past, the number that went past your point is equal to the frequency. It's sort of almost the how frequently a wave passes, if you like, then extended out in a 1 second interval. It is tied up in the time period by being this. So F, the common symbol at GCSE for frequency, is 1 over capital T, which is going to be what I'm going to call the time period. And that's because if a wave takes half a second to go past a point, to travel past a point and for one full cycle, the period being, of course, the time it takes for one full cycle, then if it takes half a second to go through that cycle as it passes a point, then 2 full cycles will pass a point in a second, so the frequency is 2. And the unit is actually seconds to the -1, or more often you will see it in hertz. Now, pitch is specifically tied normally to sound waves. So you might probably have thought of how high a sound is. Sort of the high or lowness of a sound or a musical note, if you're someone who's musically minded like me. But it is very much tied up in frequency, just like time period is. So if you were able to get a simulation of an oscilloscope and sort of fiddle with a wave to create a sound out of your speakers using like twiddling an oscilloscope, then you would find that as frequency goes up, frequency up leads to an increase in the pitch. So a sound where more waves pass per second has a higher sound to us than one where less waves pass per second. So if you were to create a wave with a shorter frequency or a higher frequency and therefore a shorter time period, then you would find the pitch of that wave went up. And we did a bit about transforming a waveform earlier, so you know what that looks like as well. But with all that said, we arrive at pretty much the end of the lesson. So make sure now to take any additional notes you would like, go back through the lesson and add to your notes and complete any missing exercises. The solutions to those will be in the description as always. Make sure to click the links there. And if you have any questions you would like to ask me, or you have any requests for a future lesson, please do let me know via the comments section below. One of the lessons I'm tempted to do following up from this is the calculations involving waves. So using this frequency formula, using wavelength and frequency together, calculating wave speed, which is quite a common set of practicals that you also do, but I'm always open to requests, so please do let me know. With all that said though, class dismissed. Thank you for watching Tactica Imperialis, and this has been my lesson on the properties of waves. I'll see you all again. Bye for now.